Hey, welcome to Ones and Zeros. My name is Ben, and today we're going to be taking a look at another video in our STM32 basic series. We're going to be taking a look at analog to digital converters and some of the ways that we can actually make use of those. Hopefully this stream is going to behave a bit better than the last one. I realized I didn't actually have audio in the last one, so looks like everything is working correctly this time. So, like I said, going to be taking a little bit of a look at analog to digital converters. Couple of things first up though, thank you to all of the new subscribers that are on Twitch and YouTube. That really means a lot that people have been watching so many of the videos. We're actually getting close to 1,000 views of the YouTube videos in total since I started. So in under 2 months, that's not too bad for this sort of content. So thank you to everyone for that. So our approach with the video today is basically we're going to look at kind of what analog signals are versus digital signals, which you may already know, but bear with us through that because I'll try and cover that fairly quickly. Then we're going to look at some of the different approaches to actually using the analog to digital converter peripherals in STM32, because there's a few different ways that you can actually go about doing stuff with them. And then we'll look at a bit of an example of how to actually get the ADC set up and get some data from it. And then lastly, we're going to go through and do kind of what we normally do and actually get a more dynamic driver written so that we can make use of the ADCs in future. So the other thing I'd just like to point out is there has been some new code bases which have been released as well up on GitHub. So if I bring up, let me just find that one. And we'll pop over to this screen here. So we can actually see that there's a few more code bases available. So we've got the one for the F769i Discovery that we've been working on in the Discovering STM32 series. We've got the one for the board that we've been using for most of the STM32 basic series, which is the F4 Nucleo 64 board. As well as the H7 Nucleo 144 board, which we've seen in previous videos. But we've also recently added the 407 Disk 1 boards, as well as the 429 Disk 1 boards, and also the F103 Blue Pill. So there will be various drivers and things getting added to those code bases moving forward. So a bit of stuff coming there, but that way, depending on what sort of device you've got, you'll hopefully find something that might fit what you want to be working with. So we'll get that out of the road for the moment, and let's take a look at some analog signals. So if we jump over to this screen, we can see we've got the oscilloscope hooked up. We've got our good old Nucleo 64 board there that we were just talking about. Some of the other stuff that we've got here, this little circuit board here is basically just a custom board that allows us to be able to break out the 3.3 volt and ground from the Nucleo 64 and share it amongst a bunch of devices, so we can have a few different things plugged in all at the same time. So it's just to make that a little bit easier. It's basically just 3 bus bars set up on a single circuit board. And then we've got some sort of analog bits and pieces here to play with, so that we can sort of see how they work as well. So first up, as we've had a look at in some of our previous videos, we kind of know what a digital signal is either off or on, right? So at the moment, the oscilloscope channel that we're viewing at the moment, the purple one, is actually hooked up to the user button on the Nucleo 64 board. So if we push that one, we can see that the signal goes low. If we release it, we can see the signal goes high. So tap that a few times, we can see that it's just a digital signal. It's either on or off. There's no sort of variation in between. So what we want to look at as far as our analog signals is something that actually gives us a bit of variation in between either on or off state. So this can be useful for things like our potentiometer that we've got set up here, as well as other things like we've got a light dependent resistor, so able to detect sort of light levels. We've also got an analog temperature sensor. This one is a, what is it, LM35, so analog temperature sensor, which we'll also have a bit of a play with. And then we've got other things like these joystick modules, which are just like the joysticks that you get in game controllers. So they actually give us 2 analog axes, plus they've also got a push button built into them as well. So these ones we're not specifically going to look at today because I'd like to do a video specific to these, because there's some cool tricks and things for those that we can use to be able to automatically deal with dead zones and all that sort of stuff to try and prevent controller drift over time. But looking at our actual analog signal, so we can see at the moment our potentiometer's turned all the way down. Our signal on the scope is all the way at 0, or we're actually getting 10.4 millivolts approximately. However, as we go to adjust this guy, we're going to see that the signal starts to rise. And we can actually, as we move the potentiometer one way and the other, we can actually see that that signal varies. So what the analog to digital converter peripheral does is it allows us to take that analog signal and turn it into a digital number. Typically, if we're looking at using a 12-bit analog to digital converter, which is the approach we're going to use today, that gives us a value in between 0 and 4095, which then gives us the ability to figure out what position that analog signal is actually at. So it can be useful for a bunch of different things. So let's jump over to this screen here so that we can have a bit of a look at our actual approach to the way we're going to be using the ADCs. So if we've got our ADC peripheral, we've actually got a bunch of different ways of being able to trigger that. So we can trigger it to do a conversion from software, excuse my messy writing, or we can use something like a timer, or we can do things where we can get it to just basically continue to do continuous conversions. So coming into this ADC, we've also got a bunch of different analog channels. And then coming out of that, we're going to have our digital data. So that's kind of our approach. Now, today what we're going to look at actually doing is making use of a timer to be able to regularly trigger the analog to digital converter to do the conversions for us. So that way it gives us a little bit more control over the regularity of when that analog to digital converter is actually doing its sampling. And using a single analog to digital converter peripheral, it does also give us the ability to be able to have multiple channels hooked up to a single analog to digital converter. So we can have up to 16 channels active at the same time. We'll just jump back to that screen there. So we can get it to step through converting one channel, then the next one, then the next one, then the next one. So it can basically have a bit of a series of them, which makes it kind of cool in the fact that we can use that one peripheral in quite a flexible way. There is also a bunch of additional things that we could get into as far as extra modes and things that it has, but we're going to try and keep it fairly simple for today. So the first things first is we're going to have a look at actually getting our potentiometer that we were looking at on the oscilloscope, basically giving us digital data that we can then print out via serial and just sort of get a feel for how that works before we actually look at going on to write a specific driver for that. So let me just grab the particular bit of code that I want for that one. Okay, excellent. So let's just get our pins changed over on the board as well, because otherwise we're not going to get any data at all once we go to start having a look at that. Just bear with me a moment. Make sure we get that one hooked up to the correct pin. So we want GPIO A pin 0, which is hiding on our list somewhere. There we go. So let's just get him connected up like that. That's that bit sorted out. You'll find these particular... I'll just jump back to that one. So you'll find these particular things that come with the Nucleo 64 board super useful as well, because they do have a bit of a breakdown of all of the pinouts and things like that, which can be really useful for making that actually work. So let's jump back to that one there. Camera seems to be acting a little bit weird, but that's okay. And let's have a look at actually getting an analog to digital peripheral setup. So we're just looking at the code from the F411 Nucleo 64 board. Not sure why that camera keeps freezing. So let's jump to that one instead. That'll do. All right. So a couple of things that we're going to need to do initially. So first thing that we're going to need to do is actually get our GPIO pin set up. That's the one I want there. So coffee's not sunk in quite enough at the moment, so excuse me if I'm a little bit slow with things. So we're going to pop a section in here just in our setup on main.cpp, so just after we're finished setting up our serial device, which gives us the data over the ST link. And let's go with setting up our GPIO for our analog to digital converter. So for this one, we're going to need our typical GPIO init type def. We'll call him GPIO init, and we'll fill that full of zeros. So our pin is going to be GPIO pin 0, because that's we're using GPIO A pin 0. Our mode for that one is actually going to be analog. We're not going to be using a pull up or pull down resistor, so no pull in for that one. And because we're not using it as an output pin, we don't actually need to set the speed. It's not actually going to make any determination on it, but I'm just kind of used to popping it in there, so we'll do that anyway. So let's get that one initialized, and this is going to be GPIO A, and we'll pass it a pointer to our GPIO init structure. All right, so that is our GPIO pin setup. Now we've got to go through and actually set up our timer that's actually going to be controlling the GPIO. Sorry, that's going to be triggering our ADC. And then we go through and set up the analog to digital converter peripheral, set up the channel which we're connecting it to, which is coming from pin A0, and then we'll look at getting some data from it. So first things first, we're going to use, I think we may use timer 4 for this one. Actually, no, we might go with timer 2. I think that one's going to work well for what we want to do here. So sorry, things keep jumping around on the screen. There we go. So as far as setting our timer up, we're firstly going to need to enable the clock for that one, like so. We'll need to initialize the timer peripheral, and we're going to need a handle for that one. So that one will be timer handle type def, and we will call this one timer handle, and again we're just going to fill that one with zeros. Alright, now a few details that we're going to need to fill out for this guy. So first up, we're going to need to know what instance it is actually using. In this case, we're going to be using timer 2. And then we're going to need to give it some initialization details. So our prescaler that we're going to use for this one, let's just go with 5,000 for the moment. And again, we can come through and we can modify all of these values at a later date as well, so it doesn't really matter too much. This is just to get an example up and running initially. So let's try and get some of this stuff tidied up a little bit. So our counter mode is going to be counting up. So basically similar to what we did with the timer interrupts video when we were talking about the timer basics. Essentially it'll count up to the value that we set for our timer period, which we'll do in a moment, and then at that point it's going to send out the trigger signal, which is going to trigger the analog to digital converter to actually do a conversion for us. So set that period, let's set that to 5,000 for the moment as well. Again, we're probably going to come back and fine tune that stuff. We'll just get it kind of up and running first up. We could actually go through and do all of the maths to figure out what that prescaler and period is actually going to give us, but we'll just take the quick and dirty approach for the moment. Now our clock division is not really going to matter too much in this instance, but again we'll chuck it in there anyway. Just going to chuck FF into our repetition counter. Probably have a bit of a look through some of our STM32 basics timer videos if you're interested in sort of understanding a little bit more about some of these values that we're chucking in here. And we also want to enable our preload of our auto reload register. Okay, so that kind of fills out the details that we're going to need to initialize the timer. Now, we're also going to need to be able to hook up the timer as a trigger to our ADC. We're also going to need a timer master config type def. The timer is basically going to be seen as a master in this situation because it's triggering a slave. So a master being the timer itself and the slave being the ADC peripheral that it's going to be triggering. So in this particular structure, we're just going to tell it that our master output trigger is going to be on our update. So every time it gets to the counter gets to the period value, it's going to trigger that update event, and we're telling it that we want that update event to be used to trigger the thing that we're kind of passing it on to. So we've also got to set up our master config synchronization. And for that, we'll pass it a pointer to our timer handle. And we'll also pass it a pointer to our master config initialization data there as well. So that's kind of got that set up for us there. And then let's set up our ADC peripheral. So similar to with our timer, first thing that we want to do is make sure that we've got the clock turned on for that one. So now, even though there's only one ADC in the Nucleo 64 device we're using, it's still considered ADC 1, so just be aware of that. Now let's go through and get that initialized. Now for this one, we're going to need a ADC handle type def, and this will be our ADC handle, and we'll go through and get the details filled out for this one. So again, we want to tell it what instance we're using, so what peripheral we're actually using, and this will be ADC 1. Not sure how much space we're going to need to get everything lined up there, so let's just start with that for the moment. So ADC clock prescaler, and we'll go div 4 on that one. Now it's going to need to know what resolution we want to use, so you can go with different resolutions as far as how fine a detail you want to be able to get from the numbers out of the analog to digital converter. So for example, if we went with 8-bit, it would give us a value of 0 to 255, depending on if we're looking at 0 volts or 3.3 volts effectively. In this case, we're going to go with 12-bit, which gives us a value in between 0 and 4095. So we get a bit more granularity over the actual signal that we're looking at there. Now, our scan conversion mode, we're going to enable that, because if we do go through and add multiple channels, we want to be able to get it to scan through those. There is also things called actually, we'll look at the continuous conversion mode first. So in this case, We could set it up, say if we had 4 different ADC channels set up, we could have it so that it's actually stepping through one after another continuously without stopping. However, in this instance, we're looking at actually using the timer to trigger each of those. So we're going to set our continuous conversion mode to disable, and each conversion is going to be individually triggered by the timer. So our discontinuous conversion mode is also going to be disabled. We need to set our number of discontinuous conversions. In this case will be 0 because we're not using those. Something we'll talk about in a bit of a future episode. So we want our external trigger conversion edge. So this is the either rising or falling edge that the conversion is going to be triggered on. So that trigger is the one coming from our timer. So we're going to go with rising edge on that one. And we've also got to tell it where the external trigger is coming from. So that should be T2 TRGO. So timer 2 trigger out. We've got to set our data alignment. So that basically sets whether if we're fitting our 12-bit value into 16 bits, whether it's going to align those 12 bits over to the left or the right. In this case, we're going to go right aligned, so that we're getting a value between 0 and 4095 specifically. Tell it how many conversions we're going to be doing. In this case, we're just going to go with 1 for the moment because we're just going to set up 1 channel for the moment, and then we might add a couple more after that. Our DMA continuous requests, we'll set that to enable. Now we could also make use of DMA to be capturing the data from the ADC and moving that over to the particular area of memory where we want to be storing the data, but in this particular case we're actually going to be doing that stuff a little bit manually as well, just so that we can sort of see that approach. I do want to get into DMAs a little bit more in future videos, but for the moment we're not going to look at that too much because it can add a little bit of confusion if you're someone that's sort of new to getting into microcontrollers. So we'll do a specific thing where we're just going to be talking about different ways that we can use DMAs. So we want to pass it a pointer to our ADC handle. And then we're going to check that that has actually initialized correctly. If it hasn't initialized correctly, then we want to turn on our user LED. And we'll print a message out of serial. Like so, and we'll also chuck it into an infinite loop because we don't really want to continue on with trying to set things up if it does fail at that point. However, if we've gotten to that point, then we can actually go through and look at getting our channel set up. And for that, we're going to need a ADC channel config type def, and we'll just call this ADC channel in it. Well, sounds good. We'll go with that. So, first thing we want to do here is tell it which channel we're actually going to be using. Now, this should be ADC channel 0, I think, if we're going with pin A0. Let's just double check that. That is correct. Wonderful. Might help if we actually type all of this stuff in correctly. Okay, so we want our rank. So our rank is which it allows us to determine what order each of the channels are in. So say if we have 4 channels, you're going to have rank 1, rank 2, rank 3, rank 4, for example, for that one. So if we have a look at this one here, so it basically treats it through, you can have up to 16 different channels set up. The first one being index 1, and the last one, if you've got all 16 of them, will be set to 16. So it's not a 0 indexed thing in this situation. So because we've only got one channel, it'll be rank 1. Our offset, we are just going to set to 0 because of how we're going to be capturing the data. And one of the important things is the sampling time. So there's a variety of different sampling times that you can use. You need to be aware that the faster you're sampling, let's just pull this up. So the faster you're sampling, so say if we set it to 3 cycles, you may not actually get accurate data from the analog to digital converter in that situation, because it may not give it enough time to be able to go through and capture the data correctly. So you'll notice that in here we've got everything from 3 cycles all the way up to 480. I'd normally try and find a good balance in between getting accurate data and being able to get the samples done quickly. Also be aware though that say if you're only sampling one channel and you only need data updating from that every second, then you'd probably go with 480 cycles so that it gives it more time to be able to capture that data correctly. Because it does take time for the ADC peripheral to actually do that conversion from the analog signal and figure out what it is as far as a digital number. So we'll go with 480 cycles for this example at the moment, and then we'll go through and configure the actual channel. So we need to pass a pointer to our ADC handle to that, and also our ADC channel init data as well. And then, same as before, if we do run into an error, we want to know about it rather than just continuing on. So just to help as far as debugging, and we might also just pop a couple of messages in here just to let us know if things are succeeding as well, because it's always nice to know that. Can't type. And we'll also want to chuck that one into an infinite loop if it fails as well. There we go. So we've got our channel set up. Now, because we're going to be using the analog to digital converter interrupt to allow us to capture the data when the conversion's complete, we're also going to need to set up the interrupt for that one as well. So I'm going to need to set its priority. And let's just go with, a value of 8 for that one. So that'll be a value between 0 and 15. We'll go somewhere in the middle with that because that'll be perfectly okay. And that last value will be 0 because of how we've got our NVIC set up. And then we'll also need to enable that interrupt as well. All right, so that's basically got us to the point where we've got our, might help if I spell that correctly, there we go. That's got it to a point where we've basically got our peripheral set up. So we've done our GPIO, that's good to go. We've set up our timer that's going to be triggering our ADC peripheral. We've set up the ADC peripheral itself. We've told it that we did the particular channel information that it needs to be able to configure that channel and have that being able to gather data from the GPIO pin. And then it's going to be a matter of actually going through and getting everything started from that point. So basically getting everything turned on so that stuff is actively happening. So if I find the particular bit I'm looking for there, so we're going to want HAL ADC start IT to start the actual conversion process for the ADC itself, but it's not going to do anything until its trigger source is actually enabled as well. So in this case, we're going to go through and enable our timer as well, which should then start all of that ball rolling. Now, a couple of other bits that we're going to have to do first. We're going to have somewhere to store the data. So we're just going to create a global up here. And let's just call it ADC temp data. Chuck a 0 in it initially just because we can. Now we're also going to want to get our actual interrupt handler sorted out in here as well. So I believe it's just going to be ADC IRQ handler. Let's just double check that one. Yeah, so name of that one's just going to be ADC IRQ handler. So we're on the right track with that. I'll pop this one down here. Now, I'm not going to worry too much about commenting everything at the moment. As you may have noticed, there has been a lot of different comments added to the code bases that are going up on GitHub. So as far as even the driver that we're going to look at writing during this video, all of the commenting for that is going to happen outside of this actual video, so that you guys don't have to sit through watching me type a whole bunch of stuff for that. Now for our handler in here, we're first going to need to check if the end of conversion flag has actually been triggered. Now we're going to need to be able to access a couple of things from here in order to do that. One of them is going to be our ADC handle. So we're actually going to grab that, and we're going to make that a global as well. The reason for that is because then grab hold of both of those, jump into our handlers file, and we can use extern to give us access to those particular details from our IRQ handlers file, so handlers.cpp. So we want to be able to pass the ADC handle to this one so that it knows which ADC we're asking about. Part of the reason for that is because some of the F7 devices and things, I think even some of the F4 devices have multiple ADCs, up to 3 of them for some of the devices. So we're also going to need to make sure that we clear that flag as well. All right, now in between here is where we actually want to go through and capture the data. And for that, it was just ADC temp data that we used, yep. So ADC temp data. And in this case, we're just going to extract the data directly from the ADC data register. So we can use our ADC handle for that. We'll go for the instance, which then gives us access to all of the various registers directly, and we're going to go for the data register. So basically copying the data register directly to ADC temp data. Now that's got our interrupt sorted out there. We've got all of our initialization done. Now let's just rename that guy because we can actually reuse him. And we're going to set this to 1000. So every second we're going to get it to print out the current analog to digital data via serial for us. Do have, cool, that's all good there. So we go down into our processing loop. We'll set up a sort of task timing thing for this one. Call it ADC update ticks. And just make that ADC update tick threshold so that it kind of matches. We'll keep the naming schemes common between them, make life a bit easier for ourselves. So if you're curious about the particular approach that we're taking here for timing different tasks, then that's actually in the first episode of our Discovering STM32 series. So worth checking that one out because it does allow us to more effectively be able to time different tasks so that if we've got multiple different things, say we want our heartbeat LED to update every 500 milliseconds, but we want our ADC to spit out some data every second, and then maybe if we have an LCD screen, we want that updating at 30 frames a second, things like that, we can go through and actually time all of that nice and easily. So we're just going to grab we'll call this string data. I'm going to use sprintf on that one. And just get that formatted, and then we will get that to print out via serial. Now the other thing that we're going to need to do there is also make sure that we should be ADC update ticks. And I'll just subtract our ADC update tick threshold from that one. And let's see if we compile. Okay, so 4 errors there. Let's see what we've got. May have misspelled that one a little bit. Missed an underscore in those guys. And that should be tree conversion edge. And that should all be good there now. Also, might want to fix that bit up. Okay. Nope, had those named nearly correctly in the first place. Let's try that. Really not on the ball this evening. There we go. That should hopefully get rid of all the errors. Nope, still a couple left over. Where are they hiding? It's giving us an issue with multiple definitions of our handle and our why is it doing that? Bit of a curious one. Let's just give that a clean first up. Sometimes it can be a little weird. I have a feeling that bug's going to show itself again though. Okay, still 3 errors. Aha, that's because we're actually trying to initialize these guys in here as well. That makes complete sense. Let's see if it wants to behave a bit better now. There we go, wonderful. Sometimes doing the clean can be really useful as well, because sometimes there'll be certain warnings that actually get hidden. So if you've ignored a warning and recompiled, sometimes it's not going to give you the same warning again. In that situation, it can be really useful to go through and do a code clean, because any of those warnings are going to come back to the surface and you're going to be able to see them again. So in that case, that did actually help for me to figure out what I was actually missing there. So let's get that code dumped across to our device there. See if we can get our camera angle a bit more suitable for what we're looking for at the moment. There we go. I think that's going to work for us. So that's all come across. Let's pull up our serial monitor. And we can already see that we're getting data. Now we're not getting correct data, because if we go through and let's just jump over to this one. Oh no, we are actually getting so our update rate for our ADC is too slow, is what it looks like is actually happening there. Which is why it jumped from 0 to 872 and then it's sticking there. So what we'll do is let's just jump back into main and to where we've actually set up our timer. Let's just change some of those values for our timer prescaler and our period. We'll dump that software back across. Yeah, so that's the update rate for the ADC. It wasn't sampling quickly enough. So let's see how we go this time. Still seem to be running into a similar issue with that. Let's turn down our sample time. Let's just go with 84 cycles. Okay, definitely something weird happening there. If we turn it all the way up, just want to see how long it actually takes it for it to start to capture the correct data. Okay, so it's finally started capturing the right data at that point. So I'm not sure that's actually the timer that's causing that, although it may be. Let us try a slightly different approach. So we're going to go with, might even just turn our repetition counter all the way down. This is all set up correctly. And just make sure that we've got all of our other settings done correctly there as well. See single conversion, that's all correct there. And I think if our repetition counter may have been playing with that, or if it's something else. Still same issue. Okay, what have we missed? What we have missed is actually setting up our timer, which explains why we're getting the issue that we're getting. Which some of you may have been screaming at the screen telling me that I was overlooking that, but didn't quite see it in the moment. Okay, let's see if we have a bit more luck with that one. That's looking a little bit more promising. There we go. So always helps if you actually turn the timer on, guys, otherwise it's not going to trigger anything. So if we turn this all the way down, we can see it's going all the way down to 1. So because of some sort of resistance in the potentiometer or something like that, it's probably why we're not going to get an exact 0 value there. However, as we start to turn it up, we can see that our values are increasing. And we actually make it all the way mostly to 4095, so we've nearly got our full range of values working depending on where we're adjusting that one. So that is basically how we get an analog to digital converter set up and actually doing some conversion for us. Now, we could go through and look at adding additional channels and that sort of stuff. However, we'll also look at that when we go to do the actual driver as well, which we're going to start to look at shortly. So let's see if that camera is actually working, which it looks like it is now. So what we're going to do is let's just get that minimized for the moment. I'm going to take a quick bio break and then going to come back and we're going to get a dynamic driver written, much like we've done for a bunch of our other videos, so that you guys have got a driver that is going to be nice and easy to use for the various Quartz Arc code bases that we've got going on. So I shall return in a few minutes. And we are back. All right, so get some coffee happening before we get started on this. Wonderful. Alrighty, so what we're going to do initially is we're going to go through and comment out this particular code, and I'll leave this code in here just commented out for those of you that kind of want to have a bit of a look through that when it goes up onto GitHub. So this will be going up onto GitHub shortly after the stream. Let's comment out that stuff for the moment. And let's jump into our handlers file and we'll comment this stuff out as well. That one, and those globals that we set up in main. Just so that we don't get confused with some of the stuff that we're doing moving forward. All right, so basically back to how the code was when we started the stream. I'm going to get rid of that one. We'll save that file there. Now we're also going to be making use of the timer manager that we've used previously for some of our other videos, like the timer basics video, the PWM, and the rotary encoders video. So we're going to be using that timer manager to be able to hand us a timer that we can use to be able to do the analog to digital conversions as well. So we will be coming back to that. We'll close those handlers files for the moment and let's get us a driver sorted out. So I'm just going to call this QAD-ADC.hpp. We don't want a template. And we want QAD-ADC.cpp. And forgot to tell it not to use a template. Let's jump into here, grab our typical file header, pop it in here. We are, what is it, 16th of November. Wow. And this will be an ADC driver, and it is called QAD-ADC.hpp. Alright, we also need to do our prevent recursive inclusion down the bottom as well. Like so. Let's grab all of that and I'm going to copy this across to here, get rid of that stuff. Our source file is going to want to include QAD-ADC.hpp, fix up our file name in our header there. And then in here, we're also going to be wanting to include QAD timer manager.hpp because we'll need to be accessing that as well. So first things first is we are going to look at copying and pasting a bunch of stuff so that you don't have to sit there and watch me type a whole heap of it. So first up, we are going to go with some enums. So this basically allows us to select which channel in the rank. So when we were talking about the rank being a value between 1 and 16 before, and being able to have up to 16 channels set up per analog to digital converter, this enum is going to allow us to index into those particular channels within our driver class a little bit easier. And we're also just putting a definition in there of what the maximum number of channels is, which we'll be using as far as generating the arrays in the driver to hold the data specific to each of the channels. So that'll make a little bit more sense moving forward. Now, there is a few other enums which we're going to pop in as well. Be nice if it kept my indenting sorted out a little bit better there than it has. All right, so for each of the channels in the rank of 1 to 16 channels that we can actually do the conversions on, we've got a bunch of different channels that we can actually select from the analog to digital converter itself. So if we jump into here in our HAL ADC file, we can see that there's a bunch of different channels available, so 0 through 18. They'll be hooked up to different pins in different ways depending on the particular device you're working with, and that stuff is available in the STM32 documentation. You'll also notice that we have a voltage reference and the ability to monitor the VBAT value. So we won't get into that too much, but VBAT allows you to monitor the particular voltage that's coming in that will keep certain things like the real-time clock and the backup domain powered in the event that the rest of the device loses power. So there's a couple of different ways you can actually power and utilize the STM32 there. Some devices will also have another channel which allows you to monitor the CPU temperature basically. So that's something that we will also have a look at in future, because that can come in handy depending on what you're actually doing with the device. So this enum basically allows us to select the particular channels a little bit easier than we could otherwise. And then we've also got some sampling time enums, which is just the same as the way we've used the sampling times before. Now, the reason why we're using these enums rather than just using these values directly from our HAL file is because it will get the compiler to actually check that we're giving it a value that is a valid value effectively. So if we try to give it something outside the enum, then it's going to basically call that out when we go to compile. We will be doing a unearthing C++ video shortly on enums, which will explain some of that stuff in a little bit more detail, but there's a reason why I use them as regularly as I do. Now, we're also going to need a init structure. So much like we've done with a bunch of our other drivers, we're basically setting up an init structure so that we can provide the details that the ADC driver is initially going to need in order to basically start getting itself set up. In this case, it's going to need to know which timer it is that's going to be triggering it, what the prescaler and the period are that we're going to be using for that timer. So much like we did just before, where we set up timer 2 with a particular prescaler and period, is basically doing the same thing. It's just going to be using the timer manager to be able to do some of that work for us. Let's fix up these indents while we're in here. That's a bit better. All right, so we're also going to need a way to hold data for a particular channel. So partially as an initialization structure for that channel, so that we can actually say, we want you to set up an additional channel for the ADC. We want it to have a particular peripheral channel, so as far as which channel we're actually going to be sampling, so whether it's going to be 0 through to 18 or VREF in or VBAT, or the CPU temperature with other devices. We're also going to want to tell it what the sampling time is for that particular channel, because you can use a different sampling time per channel that's individual per channel. So you might have one channel that's being sampled at 15 cycles, one that's being sampled at 84 cycles, one that's being sampled at 480. And the ADC will actually take all of that into consideration. So what we've got for that one, and again, just to keep things simple, we'll copy and paste a little bit of this. All right, so there's basically just a structure that we've set up, which is going to tell it what GPIO port we're using and what pin we're using for that particular channel. In the event that we're using, say, vrefint or vbat, then it's automatically going to figure that out and not try and set up a GPIO pin for that. That's part of the sort of intelligence of the driver. And then, of course, what channel we're using, so 0 through to 18 or vrefint or vbat, and what our sampling time is. Now, because we're going to use this both as our initialization structure for a channel, as well as for storing data about that channel inside the driver itself, it's going to be kind of a dual use structure, which means that we want it to be nice and easy for when we call the method to actually set up a specific channel, for it to grab that data from the init structure and store it into the channel data that's in the array inside the driver. So as a result, we've set up an assignment operator there, which is basically just going to go through and copy the 4 particular bits of information from one of those QAD ADC channel data structures into another one, just by using the equal symbol, which again, we'll see that a little bit as we move forward. So losing my voice a tiny bit, so just bear with me. So let's go through and actually get, might help if I actually selected that before I copied it. Let's get our driver sorted out. Now, in the case of this particular device, so the STM32 F411 that we're using here, it only has one ADC. So as a result, we're going to set this up as a singleton class for this particular device. When we go to port it across to, say, the F769 iDiscovery, we'll actually set this driver up so that you can have up to 3 instances for ADC1, ADC2, and ADC3, so you can use those independently. But for the moment, we'll stick with it just being a singleton. Now, we're just going to call this class QAD ADC, so sticking with a similar sort of naming convention that we've been using for a bunch of our other stuff so far. We'll have our private section. We're going to have our dinit mode, which we've used in a bunch of the other videos as well. So if you haven't seen any of those, essentially what this guy is going to be used for is so that if we go to initialize the ADC driver and it fails partway through, we can do a partial deinitialization so that we're back to where we started with all of the peripherals in their default state, so that it fails gracefully. Whereas if we've got everything initialized and we want to completely deinitialize, then we can use dinit full to be able to do that. So that all is stuff that will happen inside the class itself. So similar to a lot of our other drivers, we're going to want a QA init state to keep track of whether or not the driver is actually initialized. And we're also going to want a QA active state to keep track of whether or not the driver is actually running and actively doing things. We are going to want to know which timer we're actually going to be working with, as well as what the prescaler and the period are for that timer. We're going to want some HAL handles for both our timer as well as for our ADC peripheral as well. So we'll just go MS timer handle and an ADC handle type def. So again, all of this is similar to what we did when we were having a look at it just before. We are going to want to keep track of our actual channel data as well. So we're going to use that channel data structure, create an array of those. And this is where our QAD ADC max channels define comes in, because we can use that to tell it how many items need to be in that array. We'll also want to keep track of how many channels we've actually got being used at the moment. We're going to want a way of storing the data from those channels, so the actual converted ADC data. And again, we're just going to use that max channels definition for that one to make sure our array is sized correctly. And then we're going to have a data index so that as we're stepping through each conversion for each of the channels, it knows which one it's up to, so that it knows which of the MU data array elements it needs to be storing the data in for that particular conversion. So that's kind of what that one's for. Well, also that'll make a little bit more sense moving forward as well. Now, of course, because we're going to be working with a singleton class, we're going to be popping our constructor in the private section. And a few things we want to initialize in here. So we want to set our init state to not initialized. And we want to tell it that the driver is currently inactive. And we'll also take this opportunity to basically zero out our timer and ADC handles, so that they're all full of zeros. And we're going to also set our current channel count to 0, because there's no channel set up at the moment. So that's our constructor sorted. Now we're going to go through and delete our copy constructor and our assignment operator due to the fact that we're using a singleton class. Can't type. So that's our copy constructor deleted, and our assignment operator is deleted. Now we're going to need our get method, which we typically use in our singleton classes, which just allows us to obtain an instance of that singleton class so that we can actually access what's inside of it. Also going to be doing an unearthing C++ video soon on not just classes, but also a specific one on singleton classes as well, so that sort of get a bit more of an idea of some of the stuff that is sort of being used here and why we'd use it in a particular way for singleton classes. So we're going to want some initialization methods. Let's pop some lines down the bottom of the file just so we can scroll a little bit easier. So we're going to want a method to be able to initialize, and that's going to need to be handed a initialization structure which will pass by reference, and then that is then going to call out implementation init method which we will define shortly. So we're also going to want a deinitialization methods, which again is going to call our implementations dinit method. And don't need to pass anything to that one. We're going to want a handler method. So this will be the method that gets called whenever the ADC interrupt gets triggered. We're going to want some control methods. Which, let's just copy and paste those guys. Right, so we want a method to be able to start the driver, so to make it active. And to stop the driver, again, these guys are just going to call the implementation methods, much as we're going to do for most of these. We want one that allows us to add an additional channel. If we want to be able to dynamically remove a channel, then we want to be able to do that too. And we've got two remove channel methods here. One which tells it, so if we've got 16 channels set up in our array of channels in the driver that we're actually going to be working with, then we can tell it which one of those 16 we want it to get rid of. However, if we've got a specifically, so say if we set up a channel to be capturing data from VBAT and we don't know where in the array the VBAT channel is actually set up, then we can use this one where we can actually pass it to the peripheral channel enum. So this guy here, to tell it which one of the actual ADC channels that we want it to remove, and it'll figure out which one that is and then get rid of it for us. We also want a method to be able to tell us how many channels we currently have active, which is what that one's doing there. And then we're also going to want some data methods. Fix up the indenting for that. So there's three different ones here. Again, we can either tell it what index into our channel array we're going to be using to access the data. We can get the data based on what peripheral channel that's connected to. So again, 0 through to 18, or vrefint, or vbat, or CPU temperature. And then we can also select it using the QADC ADC channel enum as well. So it just gives us some different options there depending on how we want to use it, and just adds a little bit more flexibility to the driver. So again, we're going to go with a bit more copy and paste. Because it has already been a fairly long video so far, and I don't want to bore you guys too much. So then we've got all of our implementation methods here, which we're just going to fix up the indenting for. So again, we've got the imp init and the imp dinit, which are getting called from our init and dinit static methods. We've got our perif init and perif dinit, which kind of allow us to more gracefully fail if something fails during the initialization. It's part of the reason why we use those. So these ones will actually get called by our imp init and imp dinit typically. We've got the implementation of our handler method, implementations for all of our control methods, for our data methods, And we've also got a few tool methods in here, which get trigger we'll have a look at moving forward. And then we've got a couple of methods there to be able to find a particular channel. So what its index is into our channel array. And one allows us to use the QAD ADC channel enum to search for a channel, or we can search for it using the ADC perif channel enum. So those guys are partly used with get data, but also when we go to remove channels as well, they can come in handy. So that's basically our driver class laid out. Now we need to start getting some source code done in our adc.cpp. And again, just to keep things a bit snappier for you guys, let's look at doing a bit of copy and paste. And we'll sort of explain each bit as we go, rather than having to sit there and watch me type it all. So we've got our imp init and imp dinit methods. So as far as imp init, it's basically going to copy across the data from our initialization structure and store those into the driver class. It's then going to go through and check using the timer manager. It's going to ask the timer manager if that particular timer supports triggering analog to digital conversions using the TRGO or trigger out there, because not all of them support that as a feature. If we jump into our timer manager, I believe where we set that up here, it's actually timer 2 and timer 3 that have support for that particular type of triggering. There is some other different ways you can do it using capture and compare triggering, but again, we're keeping it simple. So in this instance, if you were to use this driver on this device, you'd need to select timer 2 or timer 3 as the timer that's going to be doing the triggering. Otherwise, you're going to get that QA error, peripheral not supported. It's then going to check to see if that timer is actually busy. If it's not busy, it's going to go through and register it with the timer manager to say, okay, I'm using that timer. It's also going to let it know that it's using it for analog to digital conversion. Again, so that when we go to do some of our more OS related stuff moving forward, the timer manager is going to be able to give us data as far as, you know, what each time is being used for, things like that. It's then going to go through and initialize the peripheral and store the result of that initialization, so that if the initialization has failed, it will then go through and actually deregister the timer again to say, okay, this didn't work, so I no longer need access to that timer. That way the timer manager can track that properly, and then it's going to return whether or not the initialization failed. In our imp dinit, it's firstly going to check to make sure that the driver is actually initialized, because if it's not, there's no point trying to deinitialize it. And then it's going to go through and actually deinitialize everything and deregister the timer from the timer manager, so that the timer manager knows we're no longer using that one. Now, as far as our actual peripheral initialization methods, let's grab those guys and we will pop those over here. Again, we'll just fix up our indenting and also fix up some of the styling so that it matches the way we're commenting all of the code recently. All right, so in our peripheral initialization, most of this is actually going through and getting the timer and some interrupt stuff set up. So with actually initializing the ADC peripheral itself, that can change a little depending on how many channels that we have. So that is something that actually gets done when we start or stop the driver, rather than when we do the initialization stuff. So that way, say if we want to go through and add a channel and everything's already running, we've got our ADC doing conversions with a bunch of other channels, we want to add a new channel, it can then stop the conversion, add the channel, restart all of the conversions, and the ADC peripherals automatically going to be set up ready to go for that. So we'll see that moving forward as well. But basically going through, we're enabling the clock for our timer, which we're using the timer manager to do that for us. We're going through and getting our timer set up, so exactly the same as what we did when we were messing with this in main CPP. Setting up our timer trigger, turning on the clock for our analog to digital converter, and setting up the ADC interrupts. So setting our interrupt priority and enabling that actual interrupt. Now, the other thing that we're going to have to do here is this guy. So in setup.hpp, I typically like to have all of my interrupt priorities defined in here. So we're just going to go through and define this one. And let's give him a value of A, because we're not going to be using external interrupts at the moment anyway. Now I find it handy to have all of these together so that if I do need to rearrange priorities, if I've got a bunch of different interrupts all working together, you can come into one specific place and actually reconfigure the priorities for all of the interrupts that are being used. So that's why I typically try and keep those in setup.hpp. All right, so that's the initialization basically, and then also letting it know that we are initialized, but we're currently inactive, so that the driver can keep track of that. When we go to deinitialize, the first thing that it's going to do is check whether or not the driver is currently running, and if it is, then it's going to stop it. It's going to check whether we need to do a full deinitialization. So if, for example, we go to set up our timer and this fails, this is where it'll do a partial deinitialization to sort out everything that's happened up until that point so that it fails gracefully. However, if we're doing a full deinitialization, then it's going to go through and run the extra steps to make sure, again, that when we're deinitialized, all of the peripherals, GPIOs, everything are back to where they were prior to that driver even being used. As part of the approach of starting to do things slightly more dynamically, when we go to look at what is going to eventually become Quartz Arc OS, which is basically an operating system for microcontrollers. We're going to need our handler method. So for our interrupt handler, so as we mentioned before, if we look at this handler method here, so this static method is what's actually going to get called by our actual interrupt handler. So we might even get that sorted now so that we're not going to forget about that later. So we're just going to go include QAD ADC HPP, so this is in our handlers.cpp file, and then down where we had our ADC IRQ handler before, rather than that, we're just going to go QAD ADC and call the handler from there. Now, part of the reason why we can do that easily is because we're dealing with a singleton class, so that we can actually just access it using the name of the class rather than a specific instance, like we're doing with the UART driver for the ST-Link serial. Now that's giving us, because I don't need to put void in there. There we go. Beautiful. All right, so that's that sorted. So that's going to come through and call this bit of code, which, much like we did before, it's going to check to see if the end of conversion flag has been set. If it has, then it's going to go through and store the data into the correct index of our data array. So this array that we've set up over here. And it's going to keep track of what the data index is, rolling it over as needed in order to make sure that the data for a specific channel is in the correct item of the array. And then of course we've got to go through and clear the end of conversion flag as well to let it know that we've finished with that. Now, as far as the first couple of our control methods is where things start to get a little bit more interesting. Again, we'll just fix up our indents. Which is that one there. And we'll fix up these guys. All right, so these are the implementation methods for starting and stopping the driver. So the first thing that we want to check when we go through to actually start the driver is the driver currently started? Because if it is, we don't need to try and start it again. And if we've got at least one channel that has been set up so that we can actually go through and start doing some conversions, because there's no point setting the ADC up if we've got no channels to actually do conversions for. So it just checks that and then returns QA fail if it's not good to go. Go through and get our ADC set up. Again, you'll see we're using pretty similar setups to what we did when we tested it in main.cpp. And then we're going to go through and do the GPIO configuration, and this will go through and do it individually for each of the 16 channels. Now, I do need to go through and actually fix up a little bit of this, in the sense that if ms channels I channel is less than so it'll need to be less than vref int. Actually, we might just go, it doesn't equal QA ADC perf channel. Make sure I get the name of that correct. vref int. So basically what we want to do is make sure that if it's vref int or vbat, that it's not actually going to go through and try and set up a GPIO for it, because then we're likely to run it into a bit of an issue. So we don't want to do that for vref int or for vbat. However, as long as it's not one of those two, then it can go through and get the GPIO set up for that one. We'll go through and actually set up our channel configuration. So again, similar to what we did for our actual channel configuration here is basically what we're getting done in this section here, but again it's stepping through each of the channels that we're asking it to set up and getting each of those done specific to what channel that's being connected to, as well as what sampling time that's using there. It'll run through and actually clear the current data that's stored in our array of data for the channels, and then it's going to go through start ADC in interrupt mode and enable the timer that we're using to actually trigger that, and then of course just setting the state of the driver to currently active so that we can track that. Stop is basically doing the opposite of that, so disabling our timer, disabling the stopping the ADC. We're not actually having to do anything for channel deinitialization specifically, because when we go down further to actually deinitialize the ADC, it's going to deinitialize all of those channels as well. But we are of course going to go through and deinitialize the GPIOs that were set up for those channels as well, so that basically by the time stop has completed, we're back at the point we were before the driver was actually started. So moving on from that, we've got some of our other control methods which we were looking at before, and it's actually kept my indents this time. I like that. So this is just used to add an additional channel to the ADC. So it's first going to go through and check that we don't already have 16 channels, because if we do, we can't really go adding any more. It's going to check if the driver is currently running, because if it is, we need to stop it before we add the channel and then restart the driver so everything's reconfigured. So it'll stop that. It'll update the data for that specific channel, and then increase the number of channels we currently have. And then if the driver was already running, then it's going to go through and restart that. Removing the channels kind of similar, so checking if it's running, stopping it if it is. Then we're going to go through and remove the data for that channel. Now it's also got to shuffle some data down, so say if we had 4 channels set up and we wanted to remove our first channel, it'll actually then shuffle the data for the 3 remaining channels down 1 notch, so that everything's sitting in the array from our 0 index onwards from there. And then, of course, if the driver was already started prior to us removing the channel, it's going to go through and redo that as well. This method basically is doing something pretty similar. However, it is removing it based on the Q8E perif channel enum. So both very similar code there. Probably could have done that so that it's not as much code duplication, but for the moment it's fine, and it will probably get refactored at some point in the future. So we have our data implementation method, or methods more correctly, because we've got a couple of them. Okay, so we've got one that allows us to grab the data based on what peripheral channel we're using. So again, ADC channel 0 through to 18, as well as VREF, INT, and VBAT, or based on the actual index of that channel in the array of 0 through to 15 for our 16 channels. Definitely starting to lose my voice now, but that's cool because we are not too far off being done. The last 3 methods that we need in here are our 3 tool methods that we also popped into the driver as well. fix up our indents like so. All right, so this get trigger method just allows us to be able to return what the actual trigger value is for a particular timer, so whether it's timer 2 or timer 3, and this actually gets used up in our start methods. So this is where we call imp get trigger so that it knows which external trigger we're actually using. So that's just a tool method to enable it to be able to return a particular value for which timer is being used. And then we've got our fine channel methods that we mentioned earlier. So one just allows us to find the index of a channel in the array based on its QAD ADC channel enum. The other one allows us to do it based on the QAD ADC peripheral channel enum, which again is where we can access which actual peripheral channel is being used by that one. So that's basically all of the methods for the driver itself. So now that we've got to that point, let's include that guy in our main. Let's just build this to make sure that everything is all good at this point, and then we can go through and give it a bit of a test. Wonderful. Alright, so rather than setting up the ADC the way we did here, because all of that's now being done by the driver itself, what we can do is we'll create a global to hold the, actually no, we're using a singleton class, so I don't need a global to hold the class there for us, which is even better. So first things first is we're going to need a QAD ADC init struct to be able to set the driver up, which we'll just call sadc init. Tell it what timer we're going to use, which in this case will be QAD timer 2. These guys are defined in the timer manager HPP file. So depending on which device you're using, so for example, for converting the timer manager and some of the drivers over to the other code bases, some of the, like the F7 Discovery device, for example, has way more timers. So you'll notice that there will actually be more items in this enum for those timers. So when I'm porting those drivers across, they're getting ported across so that they're specific to the particular device as well, to make sure that that all works correctly. So we want our prescaler. Let's set that guy to 5000. That'll be our timer period, which we'll set that to 500. That sounds good for the moment. And then we'll go through and initialize our driver. And again, because we're using a singleton class, we can just access it via the class name and the 2 colons. So if that fails, then we are going to want to output a message to say that. We'll also turn on our user LED to let us know that there's an issue, and jump into an infinite loop because we don't really want to continue if that's failed at that point. We'll also, if that succeeds, we'll pop out a message via serial there as well, just to say that it has initialized. And then let's go through and actually set up some channels. So we're just going to go with one initially, and then we're going to add a couple more to it so that we can kind of see how that actually works. So we're going to need to tell it what GPIO we're using. So pGPIO. In this case, we're using GPIO A, and it's going to be pin 0, which is what we've got the potentiometer hooked up to at the moment. So GPIO pin 0. And that'll be peripheral channel 0 to connect to that specific pin. And then we've got to set our sampling time, which in this case we're just going to go with 56 cycles. That sounds pretty good. Might help if we spell that correctly. Excellent. All right, so that's filled out that information. We need to tell the timer, the ADC driver, to add that channel, and then we can just pass it a copy of that channel initialization structure. Now we're also going to go through and start the actual conversion process. So let's pop a comment in here. Just set up channels. Let's make that a little bit neater. So we're just going to go QAD ADC start, and we'll check if that actually fails. Again, if it fails, then we'll pop out a message just to say that. Turn on our user LED and jump into an infinite loop. However, if it started, we'll pop out a message saying that it has actually started correctly. Okay, now we are at a point where the driver should be up and running and ready to go. So we might actually go through and print out some data so that we can see something similar to what we're getting before. So let's keep our string as we had it before. However, this time we are going to go through and create a while loop. A for loop to iterate through the number of channels that we actually have set up, so that when we add a couple more in a moment, we can actually see the data from those as well. And then for each of the channels, might even put a carriage return in there after each group of channels, so that when we have multiple, it makes it easier to see the data that's streaming through serial.
Let's go with ADC channel
And we'll pop an I in there, so it'll tell us what channel the data is coming from and then what the data actually is. And then in order to get that data, we're just going to go QAD ADC get data and pass the index into the array there. So let's see if that wants to compile for us. Zero errors, zero warnings. All right. Let's dump that onto our device. Let's grab our... Alright, cool. So we have some data coming through. Data is accurate and it's tracking the movement of the potentiometer. So if we jump across to this one, we can see that as I adjust the potentiometer, the values that we're getting through via serial are being changed. So in order to get a couple more channels up and running, let's jump over to this one for the moment. So we've got our LDR, or light dependent resistor, that wants to focus on that maybe. There we go. So we'll give that one a try. We've also got our temperature sensor as well. So we'll give that one a bit of a try as well. So first things first is we're going to make use of the particular bus bar that we've hooked up over here to provide power to these guys. I typically wouldn't recommend doing this while you've got the STM32 powered up. It is possible to fry them if you do things incorrectly, so just be aware of that. Nothing worse than letting out the magic smoke. Get that one onto that pin. Alright, so we've got power going for both of those. So this board, as I mentioned, is basically just kind of like a 3-strip bus bar. So at the moment, the right hand edge doesn't have anything connected to it. The left hand bar is basically connected to 3.3 volts on the Nucleo device, and the middle one is connected to ground. So that just allows us to share power out to the various devices that we're plugging in here at the moment, which is why we're doing it that way. It's just a little prototype board with some pin headers soldered to it. And then we are going to use, make sure I get our actual pins correct. So grab my little pin chart thing here. So we're going to want A1, which we might go, see if we can reconfigure this a little bit. A1 will be that pin right there. And then the other one we want to go with is pin A4, which luckily enough happens to be right next to that one as well. Alright. So yeah, hang on to these guides when you get your Nucleo devices or your Discovery devices. They do very much come in handy. Alright, so we've got our potentiometer, which is hooked up to pin A0. We've got our light dependent resistor, which is hooked up to A1.
I don't have an answer for that.
We've got Siri, who thinks she wants to try and answer questions right now. And then we've got our temperature sensor, which is hooked up to pin A4. So if we jump back over to our, see if that camera wants to work a bit better. Cool. All right. And then all we have to do, because we've got the driver set up already, is we're basically just going to have to go through and set up a couple of additional channels. So this particular bit of code here, we're just going to copy and paste that a couple of times so that we can get our channel set up, and go with pin 1 and pin 4 because they're the ones that we're using for that. And then we need to tell it which peripheral channel, so that'll be peripheral channel 1 and peripheral channel 4 because that's what those pins are connected to. Again, double check the STM documentation for your specific device as to how different ADCs are set up to different pins. In fact, as an example of that, let me see if we can grab jump into my datasheet library. So if we go into our user manual for the F411 device, and we go to our pinouts and pin descriptions, scroll down a bit, we will see this pin definitions table, and we'll notice additional functions listed on the right hand side. And we can see here, for example, this pin, which is C0, is connected to ADC1 channel 10. So that's kind of how you can actually go through and figure out which ADC channels are connected to which things. So in this case, we are using pin A1, which is hooked up to ADC channel 1. We're also, for our potentiometer, using pin A0, which is hooked up to ADC1 channel 0. So that's kind of how you would go about figuring that out. And that gives us those particular settings there. So let's build that, make sure that that builds correctly. And let's dump that onto our device. We'll pull up our serial monitor, jump over to this one, and we can now see that we're getting groups of 3 channel data being streamed through. So again, if we adjust our potentiometer, you can see channel 0 has gone all the way up to the high value. If we turn the potentiometer right down, we can see that channel 0 goes right down. Channel 1 is our light dependent resistor. So if we cover that guy up, it seems that our serial has locked up. Let's just reset our device. Not sure why that locked up, but anyway, might have just been a dodgy connection. So we can see if we're covering up our light dependent resistor, we're getting a higher value on channel 1. However, if I get it into the light, we can see that value drops. So we know that guy is working correctly. And then as far as our temperature sensor, if we try and get a bit of body heat into that, again, our device has decided to lock up. There's something weird going on there. So we can see that that value has increased, so 356, 362, so that's going up. If I take my finger off that and let it cool down a bit, we'll see that value for channel 2 dropping back down. So 339, 343. So that is how we go through and get multiple channels going with that driver. I'm guessing that there is a bug with printing out the actual serial data there that I have missed, which is why we're getting that lockup. So something in here, which is a bit of a bug, but aside from that, that kind of gives you an idea of not only how to just go through and set up a ADC in a sort of a raw way like we did initially, but also to get a driver written. That code from this video will be going up onto GitHub not long after this stream as normal. However, the commenting for that driver may take a day or two for me to get finished. We do also have some other videos coming up shortly where we're going to be doing some more STM32 basic stuff. So if we jump to that camera, so essentially the next two peripherals I want to look at in the STM32 basic series is going to be the real-time clock and the random number generator. Not all devices come with a random number generator, but I find they're really cool, kind of useful peripherals. So we're going to touch on those a bit, but also coming up in that same STM32 basic series moving forward, we're also going to be starting to take a look at communications side of things as well. So as far as the testing and preparation for doing a video on SPI, that's pretty much all already done. I2C is mostly on the way, or I2C, depending on how you want to pronounce it. We may take a bit of another look at UARTs based on a particular video from or a question from a viewer. There is also some viewer questions videos coming up soon as well, so if you do have any questions, feel free to get in touch with us. I've got the contact details down there somewhere, so r/ones and zeros on Reddit is probably the best place to pop that stuff. However, you can also just leave a comment on the YouTube video or email us at onesandzeros.contact@gmail.com. Now, the other thing, as I mentioned in previous videos, the code that we're putting up onto GitHub is freely available for people to use for personal use. However, it is not available for non-commercial use on a free basis. If you do want to discuss options as far as being able to use some of the code base on a commercial product, then you will need to send us an email down on that Gmail address and we can discuss options there. Thank you so much for watching. Hope you found that kind of entertaining. If you did, would certainly love it if you gave us a follow on Twitch or a like and subscribe on YouTube. And thank you again to all of the new subscribers. You're all awesome and hope you all have a wonderful day. Thanks very much. Thanks for watching.